How does the complex build algorithm work? Everything starts with the chemical formula. As an example, let us consider a particular complex of samarium. We know that the metal is samarium, that its oxidation number is +3, and that the ligands are 3 THDs and 1 PY. Let us see how this works in the complex build algorithm. At this point, the algorithm will analyze the ligands, one by one, looking for cycles, free torsions, and defining the ligand's degrees of freedom. Let us now examine the ligand's degrees of freedom, one by one. First, the Euler angles around the geometric center of the ligands. Then, the wheel angle, which is a degree of freedom proper to monodentate ligands. And the hinge angle, which is a degree of freedom proper to bidentate ligands. Finally, movements of the ligands along with the various spherical coordinates. Now, we have a choice on how to attach the various ligands to the metal center. That is, do we want to predefine a shape for the complex or not? Let us first assume that we want to predefine the shape. In that case, we now have a number of shapes to choose from. For this samarium complex, we will choose the capped octahedron shape of code COC7. Once the central metal ion, the set of ligands, and the shape have been chosen, we must then choose one out of the point groups that are possible. And within each point group, the specific stereoisomer. The stereoisomers are, in turn, identified by their respective vertex permutations on the standardized shape polyhedron. Once all that has been chosen, the geometry can then be initialized. For a fixed shape, geometry initialization is done by anchoring each ligand to its appropriate site on the coordination polyhedron. Since the permutation vector has been explicitly chosen, information on which ligand binds to which vertex is determined. With that information, ligands can be rigidly rotated and translated to occupy their specified vertices. For mono and bidentate ligands, that information needs to be supplemented by the addition of a third point, called a reference point. Indeed, the reference point is required for the algorithm to know the correct orientation of the ligands. Here we show these reference points in green. For monodentates, this point is computed as the centroid of the atoms bound to the coordination atom. For bidentates, one partial reference point is computed for each tooth, separately. When a bidentate tooth is bound to multiple atoms, its partial reference point is the centroid of these atoms. For a bidentate tooth bound to a single atom, its partial reference point is the centroid of the atoms bound to this single vicinal atom. The centroid of these partial reference points is the final bidentate reference point. Now, we need to know the expected lengths of each of the coordinate bonds in the complex. The length of these bonds is required to correctly scale the size of the standardized coordination polyhedron, making it compatible with the composition of the coordinating atoms. That is achieved by consulting predefined tabulated values for each pair of lanthanoid ion and coordinating atom. This is done to ensure that, upon docking, the orientation of the ligand will be the correct one. Once that is known, counterpart reference points have to be also defined for the vertices of the shape. Once both sets of reference points have been determined, vertices, teeth, and reference points are paired up in accordance to the permutation vector. Given that the ligand may be in any arbitrary orientation in the database, it is evident how the reference point is required to dock the ligand at its vertices in the correct orientation. This completes the geometry initialization for complexes of fixed shape. Now, let us turn to the case when we do not want to predefine the shape. In this case, the initialization is done differently, since there is no information about vertices and polyhedra to use. The basic idea in the free shape initialization is to generate the positions for the ligands to attach themselves around the metal ion. Unlike the vertices of the coordination polyhedron, chosen when we know the shape, these points are not the positions of each ligand's teeth. Actually, they correspond to the barycenters of each ligand around the metal ion. These initialization points are expected to be as far apart as possible from one another, but are constrained to the surface of a sphere. The task of evenly spreading points on the surface of a sphere is a known mathematical problem, with many non-unique and different acceptable solutions. Since there is no single and closed-form way of doing this, we chose a method that suited us best. This method uses the Fibonacci lattice projected onto the surface of a sphere. At first, the Fibonacci lattice defined in the Cartesian space is projected onto the unit disk, which then allows the projection onto the unit sphere. Notice that, when projected on the surface of a disk, the Fibonacci spirals determine, for example, the spread pattern of seeds on a sunflower's top. This is part of the survival strategy of sunflowers. By using Fibonacci spirals to place its seeds atop its flowerhead, the developmental biochemistry of the plant achieves the most evenly packed disposition possible. We hope this illustrates why Fibonacci spirals were chosen to dispose our ligands around the coordination sphere. The method is good enough to approach known canonical solutions to the problem. For instance, our example complex with 4 ligands generates an approximate tetrahedral spread. It is well known that for some even numbers of vertices, the problem of spreading points on a sphere has the Platonic solids as solutions. The method also performs well in instances for which no canonical solutions are known, like the case for 11 points, for which no Platonic solutions exist. It is evident that an adequate arrangement of ligands has been achieved using this method, even for 11 points. At first, the ligands are placed unnaturally far from one another to avoid cluttering the coordination sphere. This must be done in order to prevent ligands from piling disorderly atop one another during the initialization phase. Once the ligands are in place, they are rotated to face the metal center with their teeth. That ends the geometry initialization. Once the geometry has been suitably initialized, with or without a predefined shape, its optimization takes place. This optimization is carried out by minimizing a function we call crowding. Crowding is a quantity that determines the quality of a metallic complex geometry. You can think of it as a very simplified molecular force field, customized to the peculiarities of metallic complexes. However, crowding has 2 main differences from a force field. The first is that it does not aim to mimic the real interactions. Indeed, Crowding focuses on obtaining good starting structures for more accurate molecular modeling computational chemistry methods. The second difference is that crowding has no numerical parameters, it is the same function for each and every complex. Now, let us examine what crowding really is. Crowding is defined in the space of the accessible degrees of freedom of the ligands. And crowding is a sum of two terms, the steric congestion and the coordination warp. The steric congestion simulates the repulsion between ligands around the metal center. It makes two assumptions. First, it assumes that all the atoms are repelling one another all the time. Second, it assumes that non-hydrogen atoms repel twice as much as hydrogen atoms. Warp simulates the attractive interactions between the coordinating atoms and the metal center that gives rise to the coordinate bonds. Warp behaves as though a set of springs is holding the coordination system in place. For complexes with a predefined shape, the springs are placed along the edges of the coordination polyhedron, preventing the coordinating atoms from leaving their assigned three-dimensional position. For complexes without a predefined shape, the springs are placed only between the coordinating atoms and the metal center so as to maintain the appropriate coordinate bond lengths while allowing the ligands to diffuse laterally during the crowding optimization. The coordination warp is a measure of how much elastic potential energy is stored in these imaginary springs. Notice that steric congestion and coordination warp are opposing influences. Sure, to minimize steric congestion, the algorithm would have to place the ligands infinitely far apart from one another. But that would infinitely deform the coordinate bond lengths and shape. So, to preserve the integrity of the coordination, a certain degree of steric congestion is inevitable and has to be accepted. Therefore, it is precisely in the balance between these two opposing influences that the complex build algorithm finds its final structures. Crowding is optimized in the space defined by the degrees of freedom that are accessible to the ligands. Depending on the allowed degrees of freedom and whether the optimization is local or global, the algorithm allows for up to 6 different types of optimization. 4 of them perform trust region local optimizations, and the other 2 attempt to perform global optimizations using the basin hopping algorithm. Depending on the choice of optimization method, other compatible degrees of freedom will be assigned to each ligand. For example, internal free torsions are always optimized for all ligands in every method. On the other hand, hinge angles, together with wheel angles, will not be available for complexes without predefined shapes. Once we have the final geometry, even when the shape is not predefined, coordination chirality can be recognized by the algorithm. Coordination chirality is recognized using the Marcus algorithm to compute the similarity between a coordination polyhedron and its mirror image. For complexes with predefined shapes, the information about chirality of the coordination polyhedron is known in advance from the stereoisomer database. However, in complex build, the chirality of the coordination polyhedron can also be assessed without explicitly knowing which shape and coordination stereoisomer it represents. It is only necessary to decide whether or not the coordination polyhedron is superimposable on its mirror image. No matter how complicated the complex, its coordination chirality is a property of its coordination polyhedron alone, not a property of the entire molecule. It is analogous to the fact that an asymmetric carbon is chiral, no matter the specific chemistry of the groups bound to it, as long as they are all different. This is why the first step to the Kohn-Ingold prelog rules is to obtain the precedence index of each atom bound to the carbon, essentially simplifying all of the complicated chemistry of the attached groups into a single number that is relevant to the chirality of the stereogenic carbon. Complex build operates with a similarly simplified representation of the ligands around the often stereogenic metallic ion. In this simplified representation, each tooth is a vertex. Each tooth that is chemically equivalent to another has the same color. The distances of these vertices to the center are normalized to unity. It is this simplified and normalized representation that complex build uses to test for the chirality of the coordination polyhedron. The algorithm starts by constructing the mirror image of the coordination polyhedron. This image is then randomly rotated. Finally, based on proximity, each vertex of a particular color in the original structure is paired to another vertex of the same color in the mirror structure. Based on this pairing, the two structures are rigidly rotated until the RMSD between both structures becomes minimal. Many such pairings will produce poor superpositions, even for complexes that are not chiral. This is expected due to the stochastic nature of the algorithm. The algorithm cycles through all of these steps, producing reflections, randomly rotating, assigning positions, and attempting to superimpose the structure to its rotated mirror image for up to 10,000 cycles. If the algorithm reaches 10,000 cycles without ever succeeding to superimpose the polyhedron to its rotated mirror image, then the complex is pronounced as chiral. For some polyhedra, the algorithm manages to superimpose its rotated mirror image. When that happens, it is because there is a particular vertex association that matches the two structures perfectly. When such a good superposition is found, then the algorithm stops. And the polyhedron is classified as not being chiral. Because the algorithm is stochastic, the absolute certainty that a structure is chiral is only achieved asymptotically with the maximum number of iterations. However, for practical purposes, our numerical experiments have shown that 10,000 iterations are enough to establish the chirality of a structure. So, now you know how the complex build algorithm works. More information about the algorithm and its software is available in our website, complexbuild.sparkle.pro.br. Thanks for watching this video. We kindly ask you that, if complex build proves to be useful in your research, that you please do not forget to cite our article. Citations are your way of supporting our work. Have a nice day.